Interruptions. Okay, if I have got an object that has got 1 kilogram of mass and I've got another object that is 1 kilogram of mass, I give them both 100 joules of energy and I give this 100 joules of energy. This one increases in temperature by 1 degree Celsius, this one increases in temperature by 2 degrees Celsius. Which one has got a smaller specific heat capacity? Kian?
The one on the right.
Why?
Because it's taking less energy for 1 kilogram to go by something like 1.
By 1 degree Celsius. What is the specific heat capacity of this object over here? It has gone up by 2 degrees Celsius after 100 joules has gone in. So, if the specific heat capacity is the amount of energy required to increase 1 kilogram by 1 degree Celsius, then the specific heat capacity of this is 50 joules. The specific heat capacity of this is 100 joules per kilogram degree Celsius. Okay, so this is the specific heat capacity, the amount of joules per kilogram degree Celsius. We can also talk about specific latent heat. Here is an axis. On the x-axis we're going to have time. On the y-axis we're going to have temperature. This is a true graph for any pure substance. If I have got the same amount of heat energy being given to an object, let us say that it is a cube of ice. If I've got the same amount of heat energy being given to that, let us say that it is 50 joules every second, so 50 joules per second, 50 watts of heat energy being transferred to it, the temperature of my ice is going to increase. It will increase up until a point when it starts to level off. At this leveling point, the temperature is not increasing. It is still getting energy, but the temperature is not increasing. That is because here we have got a change of state. The energy being supplied will not increase the temperature. The energy being supplied will cause a change of state. After the state changes happen, the temperature will increase again until we get to another flat bit. Here we have got our state change occurring. For pure substances, the change of state will always happen at the same temperature. This is water, and this is water going from a liquid to a gas. So what temperature is this? What's the temperature at which water boils? Go on, Kim. 100 degrees Celsius. Okay, that is a set temperature. The water will not get hotter than 100 degrees Celsius. Steam is therefore hotter than boiling water, because steam, being liquid water, will be at a higher temperature. Okay. The energy supplied to my ice cube for that portion of the graph is the specific latent heat. It is the temperature required to change the state of an object, to change the state of a substance. So the latent heat is the heat that is going into the object without increasing the temperature. All right, Rosie? The latent heat is the heat that's going into the object that is changing its state from a solid ice cube to a liquid puddle. The latent heat is the amount of heat needed to turn this from a solid into a liquid. The specific heat capacity is the amount of temperature required, the amount of energy required to increase the temperature by 1 degree Celsius. And it's as simple as that. Okay? The other thing we need to know for specific heat capacity is how do we find the specific heat capacity for a cup of water? Here is my water. I need to find the specific heat capacity of this. So I'm going to use the equation. Q is equal to mc delta theta. M stands for mass, C stands for specific heat capacity, delta theta stands for change in temperature. Q is the symbol that we use for the amount of energy that is going into my object. I'm trying to find the specific heat capacity. The M stands for, anybody want to shout it out? What does M stand for? F equals M times A, GP equals mg delta H. MMM stands for? Mass, lovely. And delta theta, anyone tell me what delta stands for first off?
Change.
Thank you. And what does theta stand for? Temperature, lovely. Measured in what? Kelvin or degrees Celsius? No, it doesn't matter either one, just temperature. I want to find the specific heat capacity of this cup of water. I should probably label that as water because I am not an art teacher. I want to find the specific heat capacity. What are the things that I then have to measure that will allow me to do this calculation? Go.
Is it the mass of the cup without water and then the mass of the cup with the water?
Very good. Mass of the cup and mass of the water. What else am I going to have to measure? Go on, Mr. Greg. You can find one thing up there that you can measure with something.
Temperature.
Temperature. What would you measure temperature with? Fantastic. A digital thermometer or an analog thermometer?
Digital. More accurate.
Fantastic. More accurate and also easier to read. So 2 points there straight away. Anything else that I can measure?
How much energy?
How much energy? What would I use to measure how much energy?
Joule meter.
Say it again.
Joule meter.
Joule meter. Okay, fantastic. Joule meters I don't have. I don't have joule meters here at Winterford Holtby Academy. However, I can use this equation. E is equal to V times I times T, which will allow me to measure the amount of energy that's going into an immersion heater. So we're going to skip past this, and we're going to do to this. So C is equal to Q over M delta theta. The specific heat capacity is equal to the energy transferred over the mass times the temperature, okay? This is very easy to measure because it's mass. This is very easy to measure because it's changing temperature. However, how are we going to find Q? I'm going to have a power pack, and it'll be at 6 volts, and I'm going to connect that to, I'm going to put a big box here and just say heater. That heater is going to be connected to a voltmeter, and I'm also going to include myself an ammeter. And beside this whole rig, I'm going to have myself a stop clock. I can now calculate Q because I have got the voltage, the current, and the time. Do you remember this equation? E is equal to V times I times T. So if I leave this on for 60 seconds, and the average amount of current going through is 2 amps and the voltage is 6, can you tell me how much energy I have transferred to my heater? 6 times 2, 12 times 60.
720.
Fantastic. For doing that, 7,200 or 720?
720.
Okay. I've now figured out. That's Shane. Now figured out the Q, I've got the M, I've got the delta theta, so I can figure out the specific heat capacity of the cup of water, this green water apparently. My heater will be inside my cup of water, and that's that. Core practical, specific heat capacity. Definition of specific latent heat, being the amount of energy required to change the state, and the idea of specific heat capacity. Okay? Any questions? Okay, 7-minute lesson 6, not 10. Bye-bye.